we begin today's seminar presentation on the research conducted regarding reinforcement learning-based autonomous driving driver model data analysis. Oh, the presentation will proceed as follows. First, project summary. Second, the research objective and an overview of reinforcement learning. Third, driving data analysis. And final, the project outcomes. I began by analyzing the fundamentals of reinforcement learning. Then I analyzed the variables in track driving data and compared them with the simulation data models. My inner goal was to create a reinforcement learning model to optimize racing performance. However, the goal was shifted to collect data through driving dissimulation and quantitatively analyzing the driving data of skilled and unskilled drivers. To understand the to understand the concept of reinforcement learning, I initially analyzed the research paper related to related to the reinforcement learning model development. One of the reinforcement of learning models used in this research is SAC algorithm. Before explaining the SAC algorithm, I will briefly discuss the Q-learning algorithm as this part overlap with my previous seminar. The Q-learning algorithm is a method where the agent learning the value of action in a given state. By updating the Q values, it proceeds to learning the optimal action policy. Here, the Q value represents a numerical value indicating how good a particular action is. The SAC algorithm is an open of policy optimization algorithm based on maximum entropy reinforcement learning. The term maximum entropy here refers to encouraging maximum uncertainty to ensure diverse exploration. A representative concept explored by SAC is interpolating between policy optimization and Q-learning, which aims to find the middle ground between these two approaches. Next, I compared the Q-learning and DQ network algorithm using a multiple exam. By adjusting the parameters of each algorithm to keep the power from falling, the results showed that DQN demonstrated superior performance. This is because DQN is better suited for handling continuous state space and efficiently stores and reuse past experience through the replay buffer. Thanks to these characteristics, the can achieved better results compared to currently. Originally, I planned to use the represent, reinforcement learning algorithm and Tony's early to create our driving model and energize how much it differs from actual human driving by examining graphs, and performance quantitative analysis. However, for this part, the driving simulation was conducted by the human. Humans were treated as agents, assuming they were also running during the simulation. Before driving into the driving data analysis, I selected five keys data type from the available data. The 2D country coordinators represent the driving trajectory. The steering angle indicates steering performance. The CG acceleration shows the vehicle acceleration. The ground speed reflects speed maintains, and the trip slip angle represents grip changes. I analyzed the data by comparing graph using MATLAB. The driving vehicle used was Hyundai Avante AMD, and the results are based on 10 circuit runs. The circuit driving data was selected from three available data sets based on the recommendation of the teaching assistant. For any analysis, a specific section of the circuit was chose and synchronized the entry and exit positions across our 10 data set by adjusting the time settings ac- accordingly. First, I evaluated the driving performance based on the steering angle data. In case of the data 1, the steering angle varia, variation section was relatively short, with quick, quick and smooth movement. Cornering remained stable even with small angle changes, as the deviation of steering inputs and the rate of steering angle changes were minimized. This resulted in the fastest lap time. On the other hand, in the data set, the length and pattern of steering angle variation were longer and more irregular compared to data 1. This indicated an increase in necessary steering inputs during cornering, making it difficult to maintain speed and learning to longer lap times. Notably, in data 6, a negative steering angle occurred around the 16-second mark, causing an unstable condition. This suggested that the vehicle was at risk of deviating from its path during cornering, requiring abrupt steering corrections. As a result, the lap time was delayed. Analyzing the CG accelerator data 1 showed relatively constant rate of acceleration with minimal fluctuation, indicating stable cornering during turning section. In contrast to the other dataset, exhibit significant fluctuation in lateral rate acceleration, ranging from -1 to 1, suggesting abrupt direction changes or sharp turns. This instability likely led to long lap times. Notably, in data 6, our sharp positive rarely acceleration peak occurred during the 15-17 second section. This indicated a sudden change in direction, causing vehicle unstable and resulting in speed loss. Next, analyzing the ground speed data 1 showed an inner speed reduction of approximately 50%, but it quickly began accelerating on allowing the vehicle to exit the cornering efficiently. While other data sets achieved their their lost speed around the 10-second mark. Data 1 demonstrated faster recover, recovery through consistent acceleration. In contrast to data 2 experienced a significant speed drop, nearly researching zero before beginning to recover. This excessive deceleration caused a delay in the acceleration phase, which ultimately resulted in the slowest lap time for that section. Hmm. Next is the tire slip angle analysis. This data represents the difference between the tire's direction of travel and the actual direction of the vehicle. In the case of data 2, a sharp change in angle occurred. Although the current data shows the front right tire similar similar slip angle variations were observed across all four tires, which likely resulted in lap time loss. On the other hand, in data 6, a positive slip angle change was observed around the 15-second mark, causing partially tire grip loss. However, the degree of change was similar compared to data 2. Nevertheless, Nevertheless, compared to other datasets, sleep angle variations were still present, indicating that these also had a negative impact on driving performance. Finally, regarding the lap times, the fastest lap time was recorded in data 1, while the slowest lap time was observed in data 2. The remaining data sets showed similar trends, which align closely with the driving data analysis results. In conclusion, although there are differences in lap time at the beginning, as the learning progressed, consistent graph patterns began to emerge. This suggests that tre- treating humans as agents was a reasonable assumption. However, factors such as human driving errors and limited driving outcomes prevented the extraction of optimal data. I believe I believe that with more driving trial, the lap time could be further improved. Thank you for listening to my presentation.